The cosmos, you see, is a magnificent illusion. Every star, every galaxy, every swirling nebula is just the visible surface of a far deeper reality. Behind the scenes, hidden from our eyes and even our finest instruments, are the true architects of the universe. These are the unseen forces, the cosmic puppeteers pulling the strings of reality itself. By the end of this journey, you will understand the 30 most powerful hidden mechanisms that shape everything from the birth of stars to the fate of all existence. We will explore why galaxies spin too fast for the matter we see, what phantom energy is tearing space apart, and how the vacuum of nothingness might hold the key to everything. Which hidden force do you think is the most mysterious? The first of these hidden architects is so pervasive it outweighs everything you can see by a factor of 5 to 1. It is the universe's greatest unsolved puzzle, a substance that refuses to interact with light yet dictates the fate of galaxies. This is dark matter. Its story begins not with a direct observation but with a glaring inconsistency. In the 1930s, a brilliant and often cantankerous astronomer named Fritz Zwicky was studying a distant cluster of galaxies. He calculated how fast individual galaxies were whizzing around within the cluster, based on the immense gravitational pull needed to hold the whole system together. The numbers did not add up. The visible stars and gas simply did not provide enough gravity to explain those speeds. The cluster should have flown apart long ago. Zwicky proposed the existence of Dunkel Materie, dark matter, an unseen mass providing the missing glue. Decades later, astronomer Vera Rubin provided the definitive evidence. She meticulously mapped the rotation of spiral galaxies, expecting stars on the outer edges to orbit more slowly, just as Pluto moves slower around the Sun than Earth does. But her data revealed something astonishing. Stars far from the galactic center were orbiting just as fast as those near the core. This meant the galaxy's gravitational hold remained strong far beyond the visible disk of stars. The only explanation was a massive, invisible halo of matter enveloping each galaxy, a cosmic scaffold holding the entire structure together. We now believe this dark matter constitutes roughly 27% of the entire mass and energy budget of the universe. It is the framework upon which galaxies are built, its gravitational wells gathering the normal gas that would eventually ignite into the stars we see. So what is it? We know it has mass and feels gravity, but it does not emit, absorb, or reflect light. It is utterly transparent. You could have a block of dark matter the size of a mountain right here, and light would pass straight through it. This makes detection a monumental challenge. Physicists are hunting for it in two main ways. The first is to try and create it. Powerful particle colliders like the Large Hadron Collider smash protons together at nearly the speed of light, hoping the tremendous energy might briefly conjure dark matter particles into existence. The second approach is to wait for it to come to us. In ultra-sensitive laboratories buried deep underground, beneath mountains to shield them from cosmic rays, scientists monitor vats of ultra-pure liquid. The hope is that, very rarely, a dark matter particle drifting through Earth will bump into an atomic nucleus in the liquid, creating a tiny, telltale signal. So far, it remains frustratingly elusive. We see its shadow everywhere in the cosmos. We map its vast structures, yet we have never directly touched it. This ghostly scaffold is the first and most fundamental unseen force, the silent partner in the dance of every galaxy. If dark matter is the invisible glue holding galaxies together, its cosmic counterpart is the phantom force doing the exact opposite. This is dark energy, and its discovery shattered one of astronomy's most fundamental assumptions. For most of the 20th century, scientists believed the universe's expansion, set in motion by the Big Bang, was gradually slowing down. Gravity, the great cosmic brake, was thought to be pulling everything back together, leading to a future of either a gradual coast or a dramatic collapse. Then, in the late 1990s, two independent teams set out to measure this deceleration by studying a specific type of stellar explosion, a supernova in incredibly distant galaxies. These supernovae act as cosmic lighthouses, their known brightness allowing astronomers to gauge their distance with precision. By measuring how much the light from these explosions was stretched or redshifted, scientists could also calculate how fast the universe was expanding when that light was emitted billions of years ago. The results were not just surprising, they were universe-altering. The distant supernova were fainter than expected, meaning they were farther away than the slowing expansion model predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was pushing galaxies apart ever faster, overcoming the relentless pull of gravity. This force was named dark energy. Think of it this way. Imagine you throw a ball straight up into the air. You expect gravity to slow it down, bring it to a stop, and pull it back to Earth. Now imagine that instead of slowing, the ball starts accelerating upward faster and faster, shooting into the sky. That is what dark energy is doing to the very fabric of the cosmos. It behaves like a property of empty space itself. As the universe expands and more space comes into existence, more of this repulsive energy appears, creating a runaway effect. This makes dark energy the dominant component of our reality, constituting a staggering 68% of the universe's total energy and matter content. Its ultimate implications are profound, pointing toward a cold and lonely cosmic fate. If dark energy remains constant, it leads to a big freeze where the universe expands forever. Galaxies recede beyond sight, stars burn out, and all activity grinds to a halt in an immense, dark, and frigid emptiness. But if dark energy grows stronger over time, it could lead to a far more violent end, a big rip. In this scenario, the repulsive force eventually overcomes all other forces, not just between galaxies, but within them. First, galaxy clusters would be torn apart, then individual galaxies, then stars would be ripped from their orbits. In the final moments, planets, molecules, atoms, and even the fabric of space-time itself would be shredded. While the Big Freeze is the more widely accepted model, the true nature of dark energy remains one of the greatest mysteries in physics. We have given it a name, we measure its effect, but we have no idea what it actually is. It is the unseen force that controls the destiny of everything, a cosmic anti-gravity woven into the void. But if empty space is filled with this repulsive dark energy, what exactly is it filled with? The answer is stranger than fiction, because at the tiniest scales, the concept of true emptiness completely vanishes. This brings us to the third unseen force, a fundamental churn at the heart of reality itself, quantum fluctuations. To understand this, you must forget everything you think you know about a vacuum. In our everyday world, empty means nothing is there. In the quantum realm, empty is the most violently active state possible. This is due to a cornerstone of quantum mechanics called the Heisenberg uncertainty principle. In simple terms, it states that certain pairs of properties, like energy and time, are linked by a fundamental trade-off. You cannot precisely know both at the same instant. For a tiny sliver of time, the energy of a point in space can be wildly uncertain. And in physics, uncertain energy is not just a lack of knowledge, it is a permission slip for reality to borrow energy and create something from nothing, so long as it pays that energy back almost immediately. This is the engine of quantum fluctuations. Across the universe, in every cubic centimeter of what you would call pure nothingness, temporary particle and antiparticle pairs are constantly sparking into existence. They are often called virtual particles. An electron and its antimatter twin, a positron, might fizz into being, exist for an almost immeasurably brief moment, and then collide and annihilate each other, returning the borrowed energy to the vacuum. This is not a theoretical fantasy. We can see its effects. The most famous demonstration is the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum, only a few nanometers apart. The empty space between the plates is so narrow that only certain wavelengths of these virtual particle fluctuations can fit. Outside the plates, all wavelengths can exist. This creates a subtle pressure difference, with more virtual particle activity pushing on the outside of the plates than the inside. The result: the two plates are gently but measurably pulled together by the restless activity of nothingness. This proves the quantum foam is real, but its greatest role was played in the first fraction of a second after the Big Bang. Cosmologists believe that the primordial universe was a seething ocean of these quantum fluctuations. As the universe expanded in a period of hyperinflation, those microscopic ripples in the fabric of reality were stretched to astronomical sizes. They became the seeds of all structure. The slightly denser patches where a few more virtual particles had flickered attracted more matter through gravity. Over billions of years, those seeds grew into the vast cosmic web of galaxies and galaxy clusters we map today. So every star, every planet, every structure you see is the magnified fingerprint of a random quantum twitch in the first moment of time. The empty space around you is not a static stage, but a boiling sea of creation and destruction, the unseen quantum static from which everything we know somehow emerged. That quantum static is the raw potential of existence, but for the universe to build anything stable from it, a crucial ingredient was required: mass. This leads us to the fourth unseen force, a field so fundamental it answers a deceptively simple question: why does anything have weight at all? This is the Higgs field. To grasp this, you need to step away from particles for a moment and think about fields. In modern physics, the primary reality is not tiny balls of matter, but invisible fields that fill all of space. The electromagnetic field is everywhere, and its ripples are what we call light. The Higgs field is another such entity, an energy field that saturates the entire cosmos. Its unique job is to interact with certain fundamental particles and endow them with mass, which we experience as inertia, the resistance to being moved. A common analogy, though imperfect, is helpful here. Picture a grand, crowded party filling the entire universe. This crowd represents the Higgs field. Now imagine different guests trying to move through the room. An unknown person, akin to a massless particle like a photon of light, can glide through the crowd with ease, barely interacting, moving at the speed of light. They have no mass, but then a famous celebrity enters. That is a particle like an electron or a quark. The crowd immediately swarms around them, clinging to them, slowing their progress. This interaction, this resistance, is what we perceive as mass. The more a particle interacts with this universal crowd, the Higgs field, the more mass it has. A top quark is mobbed relentlessly, making it very heavy. An electron gets a polite handshake, giving it a tiny mass. This field had been a theoretical prediction for decades, the missing piece in our understanding of how particles acquire their properties. Proving its existence meant finding its signature ripple. In a field, a concentrated bundle of energy can manifest as a particle. A ripple in the electromagnetic field is a photon. A ripple in the Higgs field would be a Higgs boson. Finding this particle became the holy grail of particle physics. The hunt culminated at CERN with the Large Hadron Collider. This 27-kilometer ring buried beneath the French-Swiss border accelerates protons to within a whisper of light speed and smashes them together. The goal was to recreate for a fleeting instant the conditions of the early universe, a trillionth of a second after the Big Bang, when the Higgs field first switched on. On July 4, 2012, after analyzing collisions from trillions of proton collisions, scientists announced a historic discovery. They had found a new particle with the exact properties predicted for the Higgs boson. It was not just discovering a new particle, it was confirming the existence of the field itself. This invisible ocean that permeates every corner of the universe is not passive. It is an active sculptor. Without the Higgs field giving mass to quarks and electrons, atoms could never have formed. Electrons would zip away at light speed, never bonding to nuclei. There would be no chemistry, no planets, no stars, no us. The mass it provides dictates how gravity pulls on matter, shaping the formation of every structure. So the next time you feel the weight of an object in your hand, or the effort it takes to push something from rest, you are feeling the direct influence of this cosmic field, an unseen force that turned fleeting quantum sparks into a universe of tangible things. The Higgs field gave the universe its substance, but it did not explain its shape. Why is the cosmos so vast, so uniform, and so geometrically flat on the largest scales? The answer lies in a breathtaking cosmic sprint that happened almost at the beginning of everything. This is the theory of cosmic inflation. In the standard Big Bang model, the universe started as an unimaginably hot, dense point. But that model had puzzles. The first is the horizon problem. Look at opposite ends of the observable universe. Their light has only now reached us after 13.8 billion years of travel. Yet those two regions have never been in causal contact. They were too far apart for any influence, even light, to have traveled between them since the Big Bang. So why is the temperature of the cosmic microwave background, the afterglow of the Big Bang, so perfectly uniform across the entire sky? It is as if two strangers on opposite sides of the planet were wearing identical outfits without ever having met. The second puzzle is the flatness problem. Measurements show the large-scale geometry of our universe is incredibly flat, meaning parallel lines stay parallel and the angles of triangles add up to exactly 180 degrees. For this to be true today, the density of the early universe had to be fine-tuned to an astonishing precision of 1 part in 10 to the power of 60. That is like balancing a pencil on its tip for billions of years. The odds of this happening by chance are virtually zero. Cosmic inflation solves both puzzles with a single, elegant idea. It proposes that a tiny fraction of a second after the initial moment, around 10 to the power of negative 36 seconds, the universe was seized by a bizarre form of energy, perhaps a scalar field similar to the Higgs field. This energy caused space itself to expand not just rapidly but exponentially. The universe did not simply grow, it doubled in size and then doubled again and again, over and over, at a rate far faster than the speed of light. In less than a blink, a subatomic speck of the primordial cosmos was stretched to a size larger than our entire observable universe today. This explains the uniformity. Before inflation, that tiny seed was small enough for every part to be in thermal contact, reaching a uniform temperature. Inflation then blew that tiny, smooth region up to become everything we can see, preserving that smoothness on a colossal scale. It also explains the flatness. Imagine taking a tiny, wrinkled crinkle from the surface of a balloon and inflating it to the size of Earth. That small patch would appear perfectly flat to an ant standing on it. Inflation stretched the curvature of the infant universe so dramatically that any original curvature became imperceptible, leaving behind the flat geometry we measure. But inflation's most profound gift was its amplification of the quantum static. During that hyper-expansion, the microscopic quantum fluctuations in the inflating field itself, those virtual particles fizzing in the vacuum, were caught and stretched to macroscopic sizes. These tiny ripples in energy became imprinted on the fabric of space-time. After inflation ended, these ripples translated into minuscule variations in density, slightly hotter and cooler spots. Gravity then took over, with the denser spots pulling in more matter. Over billions of years, these seeds grew into the grand cosmic web of galaxies and voids. The echo of that explosive growth is still visible today, frozen in the cosmic microwave background. scientists are now hunting for the smoking gun of inflation, a specific pattern in the polarization of this ancient light called B-mode polarization. This faint swirl pattern would be a direct signature of primordial gravitational waves, ripples in space-time generated by the violent tremors of the inflationary expansion itself. Finding it would be like hearing the faint echo of the universe's first and most powerful shout, a direct line back to the moment when our entire reality was stretched from a quantum whisper into a cosmic canvas. The echo of inflation set the stage, but the universe that emerged was filled with phantoms. Among the most abundant particles in existence are neutrinos, cosmic ghosts born in the heart of nuclear fire. For every proton in the universe, there are about 1 billion of these particles. They are created in staggering numbers by the nuclear fusion powering our sun, in the violent deaths of massive stars as supernova, and in the unimaginable heat of the Big Bang itself. Yet, despite their overwhelming abundance, they are famously elusive. A neutrino is so weakly interactive that it can pass through a light year of solid lead without a single collision. Trillions of neutrinos from the sun are streaming through your body every second, day and night, leaving absolutely no trace. They interact only via the weak nuclear force and gravity, making them nearly blind to the ordinary matter that forms our world. This ghostly nature posed a huge problem for solar physics for decades. Our theories of how the sun shines predicted a specific flux of electron neutrinos, the kind produced in its core. But when scientists built detectors deep underground to catch them, they consistently found only about 1/3 of the expected number. It seemed the sun was producing far less energy than we thought, or our understanding of stellar fusion was fundamentally wrong. The solution was not a missing sun, but a shape-shifting particle. Neutrinos come in 3 distinct types or flavors: electron, muon, and tau. As they travel through space, they do not hold a fixed identity. An electron neutrino can spontaneously transform into a muon neutrino, and then into a tau neutrino, oscillating between these 3 states as it flies. This phenomenon, neutrino oscillation, proved that neutrinos must have a tiny amount of mass, a revelation that required an update to the standard model of particle physics. The missing solar neutrinos were not absent, they had simply changed flavor on their journey to Earth, becoming types our early detectors could not see. This ability to transform makes them extraordinary cosmic messengers. When a massive star collapses in a supernova, 99% of its colossal energy is released not in light but in a torrent of neutrinos. For a few seconds, a single supernova outshines the entire universe in neutrinos. In 1987, detectors on Earth caught a handful of these particles from a supernova in the Large Magellanic Cloud, marking the first time we observed a stellar death not by its light, but by its ghostly signal arriving hours before the visible explosion. Today, giant detectors embedded in Antarctic ice or submerged in deep Mediterranean waters are listening for these faint whispers. They provide a direct view into processes hidden by layers of stellar matter, a real-time probe into the engines of the cosmos. By catching neutrinos, we are not just seeing the universe, we are feeling its deepest, most hidden vibrations. These cosmic ghosts slip through matter, but other unseen forces grip it with an invisible hand. Stretching across the vast emptiness between stars and even between galaxies are immense magnetic fields, the universe's silent scaffolding. You cannot see them, but their influence is written in the light of distant quasars and the paths of the most energetic particles in existence. These are not the simple bar magnet fields you might recall from school, but vast dynamic webs woven into the fabric of space itself. They originate in the churning motion of plasma, that fourth state of matter where atoms are ripped apart into a soup of charged particles. Wherever this electrically charged gas moves, it can generate a magnetic field through a process called a dynamo effect. Think of it like a cosmic bicycle dynamo. The rotation or turbulent flow of the plasma acts like the turning wheel, and the weak magnetic seed fields already present are the initial spark. As the charged particles swirl, they stretch and twist these seed fields, amplifying them into powerful, organized structures. This happens in the interiors of stars, in the accretion disks around black holes, and in the turbulent gas between stars. Once established, these magnetic fields become a dominant, unseen architect. Their most crucial role is in the nurseries of stars within giant molecular clouds. Gravity wants to pull these vast clouds of gas inward to form a star, but the magnetic fields threading through the cloud provide a counterpressure, a magnetic rigidity that resists collapse. It is like trying to compress a bundle of rubber bands. This magnetic pressure can slow or even halt the birth of a star, regulating the pace of stellar formation across a galaxy. Only when turbulence or other processes allow the gas to slip across the field lines, a process called ambipolar diffusion, can the collapse proceed. Without these magnetic fields, galaxies might have burned through their gas in a frantic burst of star formation long ago, leaving behind dead husks. But these fields are not just brakes, they are also the most powerful particle accelerators in the cosmos. When a star goes supernova, the shock wave from the explosion travels through the magnetized interstellar medium. Charged particles like protons and electrons can get caught in this magnetic maze. They bounce back and forth across the shock front, gaining a tremendous boost in speed with each crossing. Over time, they are accelerated to nearly the speed of light, becoming cosmic rays. These are not rays of light, but a relentless rain of high-energy atomic nuclei that constantly bombard Earth from all directions. They are so energetic that their origin was a mystery for a century, but we now know supernova remnants enmeshed in their own fierce magnetic fields are likely the primary source. So how do we map these invisible force fields spanning light years? We use a fingerprint imprinted on light itself, a phenomenon called Faraday rotation. When polarized light waves vibrating in a single plane, travels through a magnetized plasma, the magnetic field slowly twists the plane of polarization. The amount of this rotation tells astronomers the strength of the magnetic field and the density of the plasma along the line of sight. By observing this effect in the radio waves from thousands of distant pulsars and galaxies, scientists can construct three-dimensional maps of the Milky Way's magnetic skeleton. These maps reveal a stunning truth. Our galaxy is not just a collection of stars, but a complex organism laced with magnetic filaments, loops, and vast ordered fields, an invisible architecture guiding the flow of gas and the fury of cosmic rays. Magnetic fields shape the cosmos, but gravity writes the story on the fabric of reality itself. That fabric can stretch, warp, and even ripple. These ripples are gravitational waves, and their detection opened a new sense for exploring the universe. For a century, they existed only in the mathematics of Einstein's theory of general relativity. Einstein proposed that massive objects like stars and black holes do not just sit in space, they bend the very geometry of space and time around them. When such objects move, especially when they accelerate violently, they should generate waves that propagate outward at the speed of light, stretching and squeezing spacetime itself as they pass. Imagine the universe as a still pond. Dropping a pebble creates ripples. Now imagine two massive black holes, each weighing dozens of times the mass of our Sun, locked in a final death spiral dance. As they whirl around each other hundreds of times per second, they are not just moving through space, they are churning the pond of spacetime, sending out powerful ripples. For decades, these waves were purely theoretical. The distortion they cause is unimaginably tiny. A passing gravitational wave from a distant cosmic event would change the distance between objects by less than the width of a proton. Detecting such a minuscule signal seemed almost impossible. That changed on September 14, 2015. two giant facilities in the United States, the Laser Interferometer Gravitational Wave Observatory, or LIGO, simultaneously heard a distinctive chirp. The signal perfectly matched the prediction for two black holes, one about 36 times the mass of the Sun and the other 29, merging into one about 62 solar masses. In that final cataclysmic fraction of a second, the equivalent of 3 solar masses was converted directly into pure energy in the form of gravitational waves. We did not see it, we heard it. This marked the birth of gravitational wave astronomy, an entirely new way to perceive the cosmos. Before this, our view of the universe came entirely from light across all wavelengths from radio to gamma rays. Now we can listen to it. Gravitational waves are unaffected by dust or gas. They travel unimpeded from the moment of their creation. They allow us to perceive events that are completely dark, like the collision of black holes which emit no light at all. Since that first detection, LIGO and its European counterpart Virgo have heard the mergers of more black holes, and even the spectacular collision of two neutron stars, an event that also flashed with light across the electromagnetic spectrum, confirming it as the source of heavy elements like gold and platinum. But this is just the beginning of listening to the universe's symphony. Current ground-based detectors like LIGO are sensitive to high-frequency waves, the chirps and crashes from stellar mass objects. To hear the deeper notes, we must go to space. The Laser Interferometer Space Antenna, or LISA, is a future mission that will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart, connected by lasers. In the quiet vacuum of space, free from Earth seismic noise, LISA will listen for the low-frequency hum of the cosmos. Its primary target will be the slow, majestic mergers of supermassive black holes, millions or billions of times the mass of our Sun, at the hearts of merging galaxies. These events generate waves with periods of minutes or hours, a bass note to LIGO treble chirp, but the ultimate goal is even more profound. Scientists hope that with enough sensitivity, future gravitational wave observatories might detect a faint, all-pervasive rumble, the stochastic background. This would be the combined echo of every black hole merger throughout cosmic history, a cosmic static. And beyond that, there is a tantalizing possibility, detecting the primordial gravitational waves generated by cosmic inflation itself. That signal would be a direct whisper from the first infinitesimal fraction of a second after the Big Bang, a time forever hidden from traditional telescopes. We are no longer just stargazers, we have become listeners, tuning our instruments to the subtle vibrations of spacetime to hear the most violent and hidden events the universe has to offer. Gravitational waves let us hear the universe's deepest collisions, but some theories suggest we might be missing signals from realms beyond our conventional physics. This brings us to the edge of known science, to a purely theoretical and deeply strange concept, tachyonic fields. The name comes from tachyons, hypothetical particles that, if they exist, have a single defining property: they always travel faster than light. In Einstein's theory of special relativity, nothing with mass can be accelerated to the speed of light. It would require infinite energy. Tachyons flip this logic on its head. They are conceived as particles that can only exist traveling faster than light, and would require infinite energy to slow down to light speed. They are not something that accelerates past the cosmic speed limit. They are born on the other side of it. This idea, while captivating, immediately shatters one of the most fundamental principles of physics, causality, the rule that cause must always precede effect. If something can travel faster than light, then from certain perspectives, its effect could be observed before its cause. Imagine a superluminal signal, a tachyon message sent from Earth to a distant star. In some frames of reference, an observer could see that message arrive before it was ever sent, creating paradoxes where you could potentially change the past. This is why most physicists are deeply skeptical of tachyons as real, message-carrying particles. However, the mathematical idea of a tachyonic field has found a more serious, though still speculative, home in cosmology. In field theory, the term tachyonic describes a particular unstable state. A normal field, like the Higgs field, sits at the bottom of its energy potential, like a ball resting in a valley. A tachyonic field, in this context, would be perched precariously on top of a hill. This is an unstable configuration, and the field would naturally want to roll down to a stable state. This rolling action can release a tremendous amount of energy. Some models of cosmic inflation propose that the inflatoned field, the driver of that hyper-expansion, might have undergone just such a tachyonic transition at the very end of inflation. The field, having been in a high-energy, unstable state, suddenly rolled down its energy hill, and the colossal energy released reheated the universe, transforming the energy of the inflatoned field into the hot soup of particles of the traditional Big Bang. In other speculative models, tachyonic fields have been proposed as a candidate for dark energy. The idea is that what we perceive as the accelerating expansion of the universe could be driven by a tachyonic field slowly rolling toward its stable point, its energy permeating space and acting as a cosmological constant. It is a reminder that at the frontiers of physics, our language for unseen forces must stretch to accommodate ideas that seem to defy common sense. While no evidence for faster-than-light particles exists, the mathematical framework of tachyonic fields serves as a crucial tool, a conceptual playground where physicists stress test the foundations of reality, exploring what might be possible in the first instance of creation or the final fate of all space. Einstein's greatest blunder was a number he threw away. In 1917, he applied his new theory of general relativity to the universe as a whole and faced a problem. His equations described a dynamic cosmos, one that should either be expanding or contracting, but the scientific consensus of the time, including Einstein's own belief, held that the universe was static and eternal. To force his equations to match this static view, he introduced an extra term, a fudge factor. He called it the cosmological constant, represented by the Greek letter lambda. This constant acted as a repulsive force, a kind of anti-gravity that could precisely balance the inward pull of all matter, holding the cosmos in a steady state. A decade later, Edwin Hubble's observations proved the universe was indeed expanding. Einstein, realizing his original equations had been correct all along, famously dismissed the cosmological constant as his biggest mistake and removed it from his work. Yet, in a stunning twist of cosmic irony, that discarded number has returned as the leading candidate to explain the universe's accelerating expansion. The cosmological constant is the simplest possible form of dark energy. It is not a field that evolves or changes, but a fixed property of empty space itself. Imagine space as a sponge soaked with a constant, unchanging energy. As the universe expands and more space comes into existence, more of this intrinsic energy appears. This leads to a repulsive pressure that drives galaxies apart at an ever-increasing rate, exactly what we observe today. So in a profound sense, Einstein's blunder was prophetic, a mathematical premonition of a force he could not have imagined. But this resurrection comes with a colossal and deeply embarrassing problem for physics. When we try to calculate what the value of the cosmological constant should be based on quantum mechanics, the number we get is catastrophically wrong. According to quantum theory, the vacuum is not empty but seething with virtual particles, that quantum foam we discussed earlier. All those fleeting particles popping in and out of existence should contribute an enormous amount of energy to the vacuum, an energy density that would act exactly like a cosmological constant. The problem is one of scale. When physicists do the math, the predicted energy density from these quantum fluctuations is about 120 orders of magnitude larger than the value we actually observe from the accelerating expansion of the universe. That is not just a little off, it is a number so mind-bogglingly large that writing it out would require more zeros than there are particles in the observable universe. It is the worst mismatch between theory and observation in the entire history of science. To put this error in perspective, it is the difference between predicting the ocean is the size of the entire observable universe and then measuring it to be no larger than a single drop of water. This discrepancy is known as the cosmological constant problem, and it represents a glaring hole in our understanding of fundamental physics. It suggests that either our theory of quantum mechanics is profoundly incomplete when applied to gravity and the vacuum, or that some mysterious, near-perfect cancellation is happening, where the positive energy of the quantum foam is almost exactly balanced by a negative energy we do not yet understand. Solving this problem may require a revolution as profound as the ones brought by relativity and quantum mechanics themselves. The cosmological constant, therefore, is more than just a number in an equation. It is a stark reminder that the vacuum of space is not nothing, and that the true nature of that something remains one of the deepest, most unsettling mysteries in our quest to understand the unseen forces shaping reality. The cosmological constant is a ghost in the machine of physics, but the hunt for dark matter's true identity has conjured another kind of specter, one born not from a mistake but from a different kind of puzzle. This theoretical particle is the action, and it emerged from a quest to understand why the universe seems to care so little about left and right. The problem lies within the strong nuclear force, the glue that holds atomic nuclei together. The mathematics of this force, known as quantum chromodynamics, allows for a subtle symmetry violation that should make the neutron, a key component of every atom, possess a tiny electric dipole moment. This would mean a neutron has a slight positive charge on one end and a negative charge on the other, like a microscopic bar magnet with separated poles. If this were true, it would violate a fundamental symmetry of nature called charge parity symmetry, and its effects would be profound. Yet, incredibly sensitive experiments have searched for this neutron dipole moment and found nothing. The symmetry holds perfectly. To explain this puzzling perfection, physicists Roberto Pexi and Helen Quinn proposed a clever solution in the 1970s. They suggested a new, fundamental symmetry that, when broken, would dynamically cancel out this unwanted effect, sweeping the problem under the cosmic rug. Where there is a broken symmetry in quantum field theory, there is often a new particle. This one was named the action, after a brand of laundry detergent, because it was theorized to clean up a messy problem. The action, if it exists, would be staggeringly lightweight, potentially billions of times lighter than an electron, and extraordinarily shy, interacting only extremely weakly with ordinary matter. But here is the beautiful twist. The very properties invented to solve a particle physics puzzle make the action a perfect candidate for the universe's missing mass. In the hot, dense early universe, actions would have been produced in colossal numbers. Because they are so light and non-interactive, they would not clump together like ordinary matter. Instead, they would form a vast, cold, frictionless ocean permeating every galaxy, exactly the kind of halo needed to explain the rotation curves Vera Rubin measured. This ocean would not be still. Due to the collective spin of actions predicted in some models, this dark matter sea might actually behave like a coherent wave oscillating at a specific frequency. We would be awash in this ghostly tide, a wind of invisible particles streaming through us every moment, their presence felt only by the cumulative gravity of their unimaginable numbers. Detecting a single action directly is nearly impossible, but physicists have devised a clever way to listen for the choir. This is the goal of experiments like the Action Dark Matter experiment, ADMX. It uses a powerful superconducting magnet to create an intense magnetic field. Inside this field, they place a high-quality microwave cavity, a kind of tunable metal chamber that resonates at a specific frequency like a musical instrument. The theory predicts that in the presence of a strong magnetic field, an action could convert into a microwave photon, a particle of light. If the cavity is tuned to precisely the right frequency, matching the mass of the action, that single photon of microwave light would be amplified and detected. It is like trying to find a single, specific radio station in a universe of static by slowly, painstakingly turning a dial across billions of possible frequencies. ADMCs and other experiments around the world are engaged in this meticulous cosmic listening project. Finding the action would be a monumental double discovery, solving two of physics' greatest mysteries at once. It would explain the puzzling symmetry of the strong force and finally give a face, or at least a name, to the dark matter that shapes the cosmos. It would reveal that the unseen scaffold holding galaxies together is not a single monolithic thing, but a whispering sea of ultralight particles, a quantum solution written across the largest scales of reality. The action is a whisper of a solution, but the vacuum holds a roar of contradiction. Empty space is not a placid void, it is a seething reservoir of unimaginable power. This is vacuum energy, the theoretical baseline energy inherent to the fabric of reality itself. It is the direct quantum mechanical consequence of those fleeting virtual particles we discussed, the endless dance of creation and annihilation in the so-called emptiness. Every single point in space, according to quantum field theory, is a tiny, frenetic oscillator with a minimum possible energy, even at absolute zero temperature. This zero-point energy of the quantum vacuum is not just a mathematical curiosity, it should have a gravitational effect. And in Einstein's equations of general relativity, any form of energy density, including the energy of empty space, can be described by the cosmological constant. This is the profound link. Vacuum energy is the most natural physical interpretation of that constant, the engine behind dark energy and the accelerating expansion of the universe. But this elegant idea immediately shatters against one of the most severe problems in all of physics, the vacuum catastrophe. When physicists attempt to calculate the expected density of this vacuum energy by summing up the contributions from all possible quantum fields and their fluctuations, they hit a wall of absurdity. The theoretical prediction is staggeringly, incomprehensibly large. The number they get is about 10 to the power of 120 times greater than the value we actually observe from measuring the universe's expansion. To grasp the scale of this error, imagine predicting that a single grain of sand should weigh as much as the entire observable universe, and then measuring it to find it weighs, well, exactly what a grain of sand should. This is not a minor discrepancy, it is the largest mismatch between theory and observation in the history of science. It suggests our understanding of the vacuum is fundamentally flawed, or that some miraculous, fine-tuned cancellation is happening that we cannot explain. One possibility is that we are incorrectly applying quantum field theory, which works exquisitely for particle physics, to the realm of gravity and cosmology. The rules may change at the intersection. Another is the concept of supersymmetry, a theoretical framework where every known particle has a heavier superpartner. In a perfectly supersymmetric universe, the positive and negative contributions to vacuum energy would cancel out exactly, leaving zero. But we do not live in that perfect universe. Supersymmetry, if it exists at all, is broken. The cancellation would be approximate, leaving a tiny remnant that could perhaps match our observations. We simply do not know. What we do observe is the effect, a vacuum energy so infinitesimally small yet so cosmically dominant that it is pushing galaxies apart. Think of it like this: the vacuum is an ocean of unimaginable latent power, but its waves are somehow frozen, its fury muted to the faintest, most gentle pressure. That subtle pressure, however, is all-pervasive. As the universe expands and new space is created, more of this vacuum energy comes into being, leading to the runaway acceleration we call dark energy. So the greatest energy source predicted by our most successful theories manifests not as a cosmic furnace, but as a phantom repulsion, a whisper that drowns out the shout of gravity on the largest scales. Solving the vacuum catastrophe may require a revolution in physics, a new theory that seamlessly marries quantum mechanics and gravity, Until then, the energy of nothing remains the most potent and most puzzling, unseen force in the cosmos. The vacuum holds a latent power, but another quantum phenomenon suggests a deeper, more intimate connection woven into reality's fabric. This is quantum entanglement, a link so profound Einstein famously dismissed it as spooky action at a distance. It begins with a simple yet bizarre principle. When two particles, like photons or electrons, interact in a certain way, they can become entangled. Their quantum properties, such as spin or polarization, become intertwined into a single, shared quantum state. You can then separate these particles by any distance, sending one to the opposite side of the lab, the planet, or even the galaxy. Here is the astonishing part. When you measure a property of one particle, say its spin, you instantly determine the corresponding property of its distant partner. If you find one spinning up, the other is instantly spinning down, no matter how far apart they are. This correlation appears to happen faster than light, with no signal traveling between them. This is what troubled Einstein. It seemed to violate the cosmic speed limit and the classical idea of locality, the principle that objects are only influenced by their immediate surroundings. He believed there must be hidden variables, predetermined instructions the particles carried with them from the moment they split, like a pair of gloves where one is always left and the other right. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a clever mathematical test. Bell's theorem showed that if hidden variables existed, the correlations between entangled particles would have to fall within certain statistical limits. If the experiment showed correlations stronger than those limits, then spooky action was real, starting in the 1970s and culminating in ever more precise experiments. Scientists have consistently found those stronger correlations. Entanglement is not a theory, it is a laboratory-confirmed fact of nature. The particles do not carry secret plans, they exist in a shared state of potential until the moment of measurement. So how does it work? The key is that no useful information is transmitted faster than light. Imagine you and a friend each take one of a pair of entangled coins to opposite sides of the universe. You flip your coin and it comes up heads. You instantly know your friend's coin is tails, but you cannot choose the outcome and you cannot send a message with it. The randomness of your result means you cannot control what your friend sees, only that it will be the opposite. The spooky link establishes a correlation, not a controllable communication channel. This preserves the cosmic speed limit for information, but shatters our classical intuition about separate, independent objects. The implications stretch far beyond the lab. Some of the most radical theories in physics now propose that entanglement might not just be a feature of space-time, but the very thing that creates it. The idea, stemming from research in quantum gravity and holography, suggests that the fabric of space-time itself could be woven from a vast, dense network of entangled quantum bits. Where entanglement is strong, space is strongly connected. Where there is no entanglement, space ceases to exist or becomes disconnected. In this view, the geometric distance between 2 points is not fundamental. It emerges from the amount of quantum information shared between them. It is as if the universe is a cosmic tapestry, and the threads holding it together are not made of material, but of these instantaneous quantum links. This leads to a staggering possibility. The smooth, continuous space-time described by Einstein may be an illusion, a macroscopic average of countless microscopic entanglements. The big question then becomes, if entanglement weaves space together, what happens to the fabric of reality when those threads are cut? Entanglement weaves the cosmos together, but what if the force driving it apart is also a master of disguise? This brings us to a theory so cunning it could be hiding in plain sight, the chameleon field. Unlike the steadfast cosmological constant, the chameleon is a dark energy candidate with a personality. It is a hypothetical fifth fundamental force beyond gravity, electromagnetism, and the strong and weak nuclear forces, but with a unique trick: its strength depends on where it is. In regions of high density, like here on Earth or within our solar system, the chameleon field effectively shrinks into the background. It suppresses its own effects, making it incredibly weak and nearly impossible to detect with standard laboratory equipment. This is how it evades our searches for new forces, but in the vast, near-empty voids between galaxies where matter is scarce, the field relaxes its grip. It becomes long-range and potent, exerting a repulsive pressure that pushes space apart. This ability to change its behavior based on its environment, to blend in like its namesake reptile, is what makes it both a compelling idea and a formidable challenge to find. The theory elegantly solves a major puzzle: why dark energy seems to have a specific, tiny value today. The chameleon field naturally evolves with the expansion of the universe. In the dense early cosmos, it was dormant. As the universe expanded and diluted, the field awakened and began to dominate, driving the acceleration we now observe. Its behavior is not a constant, but a dynamic response to the changing cosmic landscape. So how do you hunt for a force that actively hides from you? You must outsmart it. This is where atom interferometry comes in, one of the most precise measurement techniques ever devised. These experiments do not look for the force in bulk matter where the chameleon is suppressed. Instead, they probe the microscopic emptiness within and around a vacuum chamber. The idea is to create a region of extremely low density, a tiny artificial cosmic void right here on Earth. In these experiments, individual atoms are cooled to near absolute zero and launched in a vacuum. Using precise laser pulses, scientists split each atom's quantum wave, sending it along two separate paths before recombining it. The paths experience slightly different environments, one closer to a dense material wall, the other further away in the vacuum. If a chameleon field exists, its strength would vary minutely between these two paths. This variation would affect the atom's wave, causing a detectable shift in the interference pattern when the waves recombine, like two ripples in a pond meeting slightly out of sync. It is an attempt to lure the chameleon out by creating a place where it feels safe to reveal itself. Current experiments are pushing sensitivity to extraordinary levels, probing forces billions of times weaker than gravity. They have yet to find a definitive signal, but each new result helps narrow the hiding places for this elusive cosmic actor. The search for the chameleon field is more than a hunt for dark energy. It is a test of our ingenuity against the universe's cleverness, a quest to see if the force shaping the fate of all things is also the greatest escape artist in nature. The chameleon field is a master of disguise, but another candidate for dark matter has no need for stealth. It is already a perfect cosmic shadow. These are primordial black holes, hypothetical monsters born not from dying stars, but from the raw turbulence of creation itself. In the first chaotic second after the Big Bang, as the universe expanded and cooled, regions of space that happened to be slightly denser than their surroundings could have collapsed under their own gravity directly into black holes. This would have happened long before the first stars flickered on, making them truly primordial. Their masses could range from something as light as a small asteroid to heavier than 1,000 suns, all depending on the exact conditions in that searing infancy. If they exist in vast numbers, these ancient relics could account for some, or even all, of the dark matter holding galaxies together. They would be the ultimate dark objects, emitting no light, only revealing themselves through their fierce gravitational pull. Spotting a solitary, drifting primordial black hole is nearly impossible, but astronomers have a clever tool for such a hunt: gravitational microlensing. Imagine a primordial black hole passing almost perfectly in front of a distant star. According to Einstein's theory, the black hole's gravity will warp the space around it, acting like a lens. This bends and focuses the light from the background star, causing it to temporarily brighten. The star does not twinkle, it smoothly intensifies over days or weeks as the black hole moves into alignment, peaks, and then fades as it moves away. The signature is unmistakable and does not depend on the lens emitting any light at all. Teams like the optical gravitational lensing experiment have scanned millions of stars for these telltale brightenings. They have found microlensing events, but not nearly enough to suggest that planet-sized or asteroid-mass black holes make up all the dark matter. The window is narrowing, but it is not closed. Primordial black holes of certain mass ranges, particularly around the mass of a large planet or much heavier than our Sun, could still be lurking in significant numbers. Their potential role becomes even more fascinating when we look to the centers of galaxies. We now know that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole weighing millions or billions of solar masses. How did these behemoths get so big so fast in the early universe? It is a cosmic timing problem. Primordial black holes offer a compelling solution. They could have served as ready-made seeds, born large in the first instant. These heavy seeds would have sunk to the center of the young galaxy's dark matter halo, where they began voraciously feeding on gas and merging with one another, rapidly growing into the giants we observe today. Without such a head start, it is difficult to explain how they achieved such staggering sizes in the relatively short time available. So these unseen fossils from the universe's first breath could be performing a double duty, acting as both the invisible mass shaping galaxies and the planted seeds from which their central monsters grew. They are a reminder that the solutions to our greatest cosmic mysteries may not be new, exotic particles, but ancient, forgotten giants hiding in the dark. Einstein's theory predicts that gravity is not just a pull but a twist. A massive object warps the fabric of space-time, but if that object is also spinning, it does something more remarkable. It drags that fabric along with it. This is the gravitomagnetic field, often called frame dragging. Think of it like a spoon spinning in a thick liquid like honey. The spoon does not just create a dip, it pulls the honey around itself in a slow, swirling motion. In the same way, a rotating planet or star pulls the very geometry of space and time into a gentle vortex around it. This effect is incredibly subtle, a whisper within the stronger shout of Newtonian gravity. For Earth, the frame dragging predicted by general relativity is vanishingly small. Yet, measuring it became a monumental quest to test one of Einstein's most elusive predictions. That quest was the Gravity Probe B mission. Launched in 2004, it was arguably one of the most precise experiments ever flown. The satellite contained 4 near-perfect gyroscopes, each a spinning sphere of quartz smoother than the finest jewel. These gyroscopes were set spinning and pointed at a distant guide star. In a universe without frame dragging, their spin axes would have remained locked on that star forever. But if Einstein was right, the gentle drag of Earth's rotation would ever so slowly tug those axes out of alignment. The experiment was a triumph of patience and precision, requiring scientists to account for minute disturbances from solar wind and even the minute pressure of light. After years of painstaking data analysis, the team announced their result. The gyroscopes had drifted. The measured shift matched Einstein's prediction to within about 1%. We had directly detected the universe twisting around us. While the effect is minuscule around Earth, in the realm of extreme cosmic objects, frame dragging becomes a dominant, violent force. Nowhere is this more evident than around rapidly spinning neutron stars, the dense corpses of massive stars. Some of these, called pulsars, spin hundreds of times per second. Their immense gravity combined with this furious rotation creates a spacetime vortex of staggering intensity. Matter falling toward such a pulsar does not spiral in smoothly. It gets caught in this whirling distortion like water circling a drain. This gravitomagnetic field can warp the paths of particles, channel radiation, and influence the very timing of the pulses we observe. It is a dynamic, churning component of gravity that transforms these stellar corpses into some of the most complex gravitational engines in the cosmos. The detection of frame dragging confirmed that gravity is not a static field, but a dynamic, fluid entity, one that carries the imprint of a celestial body's rotation across the universe. The universe twists with the spin of stars, but its deepest structure was forged in a moment of cosmic crystallization. This process is symmetry breaking, and it is the reason we experience distinct forces like electromagnetism and the nuclear forces today. In the unimaginable heat of the very first instance after the Big Bang, the cosmos was a realm of perfect but featureless unity. The fundamental forces we now see as separate were merged into a single, symmetric superforce. There was no distinction between the force that binds atoms and the force that governs light. As the universe rapidly expanded and cooled, it crossed critical temperature thresholds, much like steam condensing into water. At each threshold, a cosmic phase transition occurred, and a piece of that original symmetry was lost or broken. A new, distinct force froze out of the primordial soup. Think of it like water freezing into ice. Liquid water is highly symmetric. Look at a single molecule, and from every angle it looks essentially the same. It has rotational symmetry, but when water freezes, it must form a crystal lattice. The molecules align in specific, rigid patterns. In doing so, they choose one particular orientation out of the infinite possibilities they had as a liquid. The perfect symmetry of the liquid is broken, but something new and structured is born. The early universe underwent similar transitions as it cooled. The first to break was likely the force of gravity separating from the others. Then, at a temperature of about 10 to the power of 28 degrees, the strong nuclear force which binds quarks into protons and neutrons froze out. Finally, at a slightly lower but still staggering temperature, the electroweak force split into the two distinct forces we know today, the electromagnetic force and the weak nuclear force. This last breaking is intimately tied to the Higgs field. As the universe cooled past this critical point, the Higgs field shifted from a symmetric, high-energy state to its stable, non-zero state, filling the cosmos. This act not only gave particles mass, but it also broke the symmetry between the electromagnetic and weak forces, giving them their unique characters. One became the long-range force of light and chemistry, the other the short-range force behind nuclear decay. So the forces we see are not fundamental truth written in stone from the beginning. They are frozen artifacts, cosmic ice crystals that formed as the fiery symmetry of creation shattered. The very laws of physics as we know them are a product of the universe's cooling history, a permanent record of the moment it chose one specific shape over all others. Even the most profound cosmic mysteries sometimes have surprisingly simple origins. For years, a tiny, persistent anomaly haunted the edges of our solar system, a whisper that seemed to defy the known laws of gravity. As the Pioneer 10 and Pioneer 11 spacecraft sped toward interstellar space after their historic missions to Jupiter and Saturn, scientists tracking their trajectories noticed something odd. Both probes were slowing down ever so slightly more than predicted. The deceleration was minuscule, a force about 10 billion times weaker than gravity at Earth's surface, but it was constant and identical for both spacecraft, as if an unseen hand was gently applying a cosmic brake. This was the Pioneer anomaly. For over a decade, it fueled intense speculation. Could it be evidence of a flaw in Einstein's theory of gravity over vast distances? Was it the gravitational pull of unseen dark matter in our solar system, or perhaps a sign of something entirely new? It became a tantalizing puzzle, a potential crack in the foundation of physics. The resolution, however, came not from rewriting the laws of the cosmos, but from an extraordinary feat of forensic engineering and thermal detective work. A team of scientists led by Slava Turyshev embarked on a monumental effort, recovering decades-old telemetry data and even reconstructing the spacecraft's blueprints and flight software. They built a detailed thermal model of the Pioneers. The probes were powered by radioactive thermoelectric generators which produced heat as they decayed. That heat had to be radiated away into space. The team calculated that this radiation did not escape perfectly symmetrically. More heat was emitted from the back of the spacecraft's dish antenna, which faced toward the Sun and Earth, than from the front. This created a tiny but constant recoil force, a gentle push from the spacecraft's own warmth. It was the equivalent of a soft photon breeze, a pressure from infrared light itself. When this thermal recoil was meticulously accounted for, the anomalous deceleration vanished. The Pioneer anomaly was solved. It was not a new force of nature, but an old one, thermal radiation, acting in a subtle, unforeseen way. Yet, this resolution is far from a disappointment. It stands as a masterclass in scientific rigor. The anomaly was real, the data was impeccable, and the pursuit of its cause drove physicists to examine every possible angle with unprecedented precision. It taught us to listen intently to the faintest whispers from our robotic explorers, because even when the answer is not revolutionary physics, the process of finding it sharpens our tools and deepens our understanding of the unseen forces, however mundane, that act upon our creations. In the grand search for cosmic mysteries, sometimes the most important discovery is learning how to see more clearly. The solved Pioneer anomaly reminds us that the universe's whispers can have ordinary origins, but the search for a truly new whisper has never stopped. For centuries, our understanding of reality has been built on four fundamental forces. Gravity governs the cosmos, electromagnetism binds atoms and gives us light, the strong nuclear force glues atomic nuclei together, and the weak nuclear force drives radioactive decay. This four-pillar framework is the foundation of modern physics, but a haunting question persists. Is our list complete? Could there be a fifth fundamental force, a subtle interaction hiding in the gaps of our experiments, waiting to be discovered? This is not just wild speculation. The possibility is fueled by genuine puzzles. One of the most intriguing comes from the heart of the atom. When certain unstable particles, like muons, decay, their wobbling spin in a magnetic field can be predicted with exquisite precision. Recent experiments at Fermilab, however, have measured a tiny but persistent deviation from that prediction. This muon G2 anomaly suggests that virtual particles popping in and out of the quantum vacuum might be exerting an influence we haven't accounted for. Perhaps they include carriers of a new, ultra-weak force. Similarly, perplexing results have emerged from studies of how ordinary matter decays. In some rare nuclear transitions, the angle at which emitted particles fly away seems to prefer a specific direction, a hint of something beyond the standard model's four-force playbook. These microscopic clues are matched by macroscopic mysteries. We have mapped the universe's structure with dark matter and dark energy, two colossal unknowns that together make up 95% of everything. Could their strange behaviors be the fingerprints of a new force, one that acts over vast distances but remains invisible to our current detectors? This quest has driven physicists to design experiments of breathtaking sensitivity, probing realms where a fifth force might be hiding. One frontier is the world of the incredibly small, at distances less than a millimeter. Why there? Because if a new force exists, it might have a very short range, its influence fading away before we can measure it in everyday life. To hunt for it, scientists use exquisitely crafted devices like torsion balances. Imagine a tiny horizontal bar suspended by a thin thread in a vacuum chamber. On each end of the bar hangs a small test mass. Another mass is then moved incredibly close to one side. According to Newton's law of gravity, the attraction should follow a precise inverse square rule. But if a fifth force with a millimeter scale range is at play, the attraction would be slightly stronger at these tiny separations. By measuring the twist of the bar with lasers, researchers can detect deviations 1 billion times smaller than Earth's gravity. Other experiments use microscopic cantilevers vibrating like tiny diving boards to sense the faintest additional pull. So far, no definitive signal has emerged, but each null result helps map the territory where this phantom force cannot be. It carves away the possible, narrowing the search to ever more exotic possibilities. The hunt for a fifth force is a testament to physics' greatest strength, its relentless self-interrogation. It is the process of listening for a new note in the cosmic symphony, knowing that if we hear it, the entire score of reality might need to be rewritten. The search for a fifth force probes the very fabric of our reality. But what if that fabric is just a single page in an unimaginably vast cosmic book? This brings us to a vision so radical it reimagines the Big Bang not as a beginning but as a collision. This is the ekpyrotic or brain world scenario, a mind-bending idea born from the depths of string theory. In this view, our entire universe is not all there is. It is merely a three-dimensional membrane, or brain for short, floating within a higher dimensional expanse called the bulk. Think of our cosmos as a perfectly flat sheet of paper drifting in an immense, dark room. Other such sheets, other brains, could be floating nearby, each hosting its own separate universe with its own laws of physics. We are forever confined to our sheet, our three spatial dimensions. All the particles and forces we know, like electrons and light, are like ink stains or vibrations trapped on the paper's surface. They cannot leave, but there is one profound exception: gravity. In many brain world models, gravity is different. It is not a force confined to our brain. It is the geometry of the higher dimensional bulk itself. This means gravitational waves could potentially leak off our brain, spreading out into the extra dimensions. To us, this leakage would make gravity appear weaker than the other forces, which is exactly what we observe. Gravity is astronomically feebler than electromagnetism, a mystery this idea elegantly explains. But the true cosmic drama happens when these floating sheets move. Imagine our brain and a neighboring one, each a whole universe slowly oscillating in the higher dimensional void. Over eons, they could drift toward each other, and then they collide. The ekpyrotic scenario proposes that our Big Bang was not a singularity from nothing, but the aftermath of such a cataclysmic, universe-shattering impact. When the two brains smashed together, an unimaginable amount of energy was released, not in a point, but across the entire three-dimensional surface of our brain. This energy heated our universe to phenomenal temperatures, filling it with a searing plasma, effectively resetting it in a fiery rebirth. From our perspective inside the brain, it would look exactly like a hot Big Bang, a universe suddenly bursting into existence from a hot, dense state. But the origin was not a singular creation. It was a transformation, a collision in a hidden, higher dimensional arena. This leads to a staggering possibility: the Big Bang may not have been unique. If brains can collide once, they can collide again. The cyclic model of the universe suggests an endless cosmic cycle. After a collision and a hot Big Bang phase, our universe expands and cools for billions of years, forming galaxies and stars. Eventually, dark energy drives an accelerated expansion that dilutes all matter and energy to near nothingness, leaving a cold, empty, flat brain. Then, drawn by a mysterious force perhaps related to a field stretching between them, the brains move together again for another collision, triggering the next Big Bang in an eternal, repeating sequence. In this view, our entire cosmic history is just one chapter in an infinite loop of creation and destruction, with gravity acting as the unseen messenger between worlds, its subtle weakness a clue that we are living on an island in a much grander, hidden sea. Gravity's ability to leak between brains hints at a deeper truth, that information itself may be the most fundamental currency of reality. This brings us to a paradox so severe it threatens to unravel our understanding of physics, centered on the darkest objects in existence. The black hole information paradox asks a deceptively simple question. What happens to the information that defines an object when it is swallowed by a black hole? In our everyday world, information is always preserved. If you burn a book, its pages turn to ash and smoke, scattering atoms in a complex pattern. In principle, a being with perfect knowledge of physics could reverse the process, gathering every atom and photon and reconstructing the original book. The information about the letters, the ink, the binding is never truly destroyed. It is just chaotically rearranged. This principle of conservation of information is a cornerstone of quantum mechanics. But black holes, as described by classical general relativity, seem to be the ultimate shredders. Imagine you throw that same book into a black hole. It crosses the event horizon, the point of no return, and is crushed into the singularity at the center. According to Einstein's theory, the book and all the information it contained are gone forever, erased from our universe. The only properties the black hole retains are its mass, its electric charge, and its spin. This presents a catastrophic problem. Two pillars of modern physics are at war. Quantum mechanics says information must be preserved. General relativity, with its singularities and event horizons, says it can be permanently destroyed. Stephen Hawking discovered the battleground. In the 1970s, he showed that black holes are not completely black. Due to those relentless quantum fluctuations at the event horizon, they slowly evaporate, emitting a faint glow now called Hawking radiation. This radiation, however, appeared to be purely thermal, a featureless hiss of random particles carrying away energy but no information about what fell in. If a black hole evaporates completely, leaving behind only this random thermal radiation, then the information about the book, the star, or the planet that formed it is irretrievably lost. The universe would have a fundamental case of cosmic amnesia. For decades, this paradox stood as perhaps the greatest unsolved problem in theoretical physics. The resolution may lie in reimagining the very nature of the event horizon. One leading idea is that the information is not lost at all, but slowly and chaotically encoded into the Hawking radiation itself. As particles escape, their subtle quantum entanglements with the black hole's interior could imprint a scrambled record of what fell in, like turning a detailed novel into a million pieces of a jigsaw puzzle and scattering them to the wind. In principle, collecting all the radiation and understanding its impossibly complex code could reconstruct the original book. This preserves information, but in a way that makes it practically inaccessible to anyone outside. An even more radical solution comes from the holographic principle. It suggests that all the information contained within the three-dimensional volume of a black hole is not stored in its interior, but is perfectly encoded on its two-dimensional surface, the event horizon. Think of it like a cosmic DVD. The movie you experience is a rich, three-dimensional world with depth and motion, but all the information needed to create that experience is stored on the flat, two-dimensional surface of the disk. In the same way, every particle that falls into the black hole leaves a kind of pixelated imprint on the horizon surface. The three-dimensional interior we imagine is a projection, an illusion generated from this two-dimensional data. When the black hole evaporates via Hawking radiation, that surface information is radiated away, preserving the data. This principle may not just apply to black holes, but to the entire universe. We might be living in a hologram where all the events and objects we perceive in three spatial dimensions are actually encoded on a distant two-dimensional boundary. The force at play here is not gravity or electromagnetism, but an informational force, a law of conservation that seems to be woven into the fabric of reality more deeply than space or time. Solving the black hole information paradox is not just about understanding the fate of matter. It is about discovering whether information is the true bedrock of existence, the unseen script from which the entire cosmic story is read. Information may be the bedrock, but its existence hinges on a deeper, more unsettling cosmic coincidence. The fundamental numbers that govern our universe appear suspiciously fine-tuned for our existence. This is the anthropic principle, a metaphor of selection that asks why the cosmos is so hospitable to life like us. Consider the strength of the forces. If the strong nuclear force were just a few percent stronger, hydrogen would fuse into heavier elements almost instantly in the early universe, leaving no fuel for long-lived stars like our Sun. If it were slightly weaker, protons and neutrons would not bind, and no atomic nuclei would form at all. The cosmological constant, that vacuum energy driving cosmic acceleration, is balanced on a razor's edge. If it were a little larger, the universe would have blown itself apart before galaxies could form. A little smaller, and it would have collapsed back in on itself long ago. The list goes on, from the precise mass of the electron to the exact amount of dark matter. Each constant seems dialed to a value that allows for complex chemistry, stable stars, and planets. The odds of this happening by pure chance are astronomically small, like throwing a dart from across the galaxy and hitting a bullseye the size of a single atom. So what explains this cosmic luck? One interpretation is the weak anthropic principle. It states simply that we can only observe a universe capable of producing observers. If the constants were different, we would not be here to wonder about them. This is not an explanation, but a selection effect. It is like a puddle marveling at how perfectly the hole it sits in is shaped to fit its water. The hole was not made for the puddle simply conforms to the hole's shape. Our universe is the hole, and we are the puddle, but this feels deeply unsatisfying. It leads to a stronger, more speculative idea, the multiverse. If our universe is just one bubble in a vast, perhaps infinite, cosmic foam of universes, each with its own random set of physical constants, then the fine-tuning mystery evaporates. In this endless landscape, most universes would be stillborn or barren, with forces too weak or strong for any structure. But by the sheer law of large numbers, a few would, by pure chance, land on the winning ticket. We inevitably find ourselves in one of those rare, life-permitting bubbles, not because it was designed, but because we could not exist anywhere else. The multiverse acts as the ultimate unseen selector force, a cosmic lottery machine that churns out countless realities, with our conscious observation acting as the filter that makes one particular set of numbers visible. Some physicists take this further, suggesting that in a truly infinite multiverse, every possible configuration of matter and energy must occur somewhere. There would be universes almost identical to ours, except where you chose a different breakfast this morning, and universes made entirely of sentient clouds of gas. This idea stretches the fabric of logic, but it provides a mechanistic, if dizzying, answer to the fine-tuning riddle. The anthropic principle forces us to confront a humbling possibility. The laws we so meticulously measure may not be fundamental truths written in the cosmos, but merely the local bylaws of our particular cosmic neighborhood, with a true, unseen multiverse operating under rules we can scarcely imagine. The fine-tuning of our universe suggests a cosmic lottery, but what if the winning ticket left behind physical scars? Among the most exotic relics predicted by cosmology are cosmic strings, hypothetical defects in the very fabric of reality, frozen in time from the universe's first moments. When the hot, symmetric early universe cooled and underwent those critical phase transitions, breaking its perfect symmetry, the process may not have been perfectly uniform. Think of water freezing on a pond. As ice crystals form and grow, they meet. At the boundaries where different crystal orientations collide, lines of defects can form like the cracks between tiles. Cosmic strings are the cosmic equivalent of these cracks, but forged in the fiery transitions of fundamental forces. They are not strings made of atoms, but incredibly thin, tube-like defects in the structure of space-time itself, regions where the energy density of the primordial fields remains trapped at its original high-energy state. A cosmic string would be thinner than a proton, yet so dense that a single inch of it could weigh as much as a mountain range. Their gravitational influence is not like that of a planet or star. Because they are essentially one-dimensional objects of immense density, they warp space-time in a unique way. Space around a straight cosmic string is not simply curved, it is sheared. Imagine cutting a wedge out of a piece of paper and taping the edges back together. The paper is now conical. A straight cosmic string does something similar to the space around it. If you were to travel in a perfect circle around a string, you would find that the total angle you traverse is less than 360 degrees. This bizarre geometry has a startling optical consequence: gravitational lensing. But unlike the fuzzy rings created by massive galaxies, a cosmic string would create a very clean, very sharp effect. A string passing between us and a distant galaxy could create two identical, undistorted images of that galaxy, side by side in the sky, a perfect cosmic double. It would be a ghostly duplication, a signature of a flaw in space itself. Even more tantalizing is their potential imprint on the oldest light we can see, the cosmic microwave background. A moving cosmic string vibrating through the early universe would have created sharp, linear discontinuities in the temperature of this afterglow. It would be like dragging a knife through the smooth surface of a pond, leaving a faint but distinct wake in the radiation. Scientists have meticulously scanned the cosmic microwave background maps from missions like Planck, searching for these telltale edges or step-like jumps in temperature. While no definitive detection has been made, the search continues because finding a cosmic string would be like discovering a fossil from the universe's infancy. It would be direct, physical evidence of those symmetry-breaking phase transitions, a frozen snapshot of the moment the forces of nature split apart. These theoretical defects are more than just mathematical curiosities. They are potential scars from the birth pangs of physics as we know it, silent filaments that could still be threading the cosmos, waiting to be seen. The fine lines of cosmic strings are theoretical, but a far more tangible rule ensures the universe is not a formless blur. At the very heart of matter, an unseen law of refusal gives everything its shape and solidity. This is the Pauli exclusion principle, a quantum decree that says, in essence, you cannot be here if I am. It applies to a class of particles known as fermions, which includes the building blocks of atoms, electrons, protons, and neutrons. The rule is simple but absolute. No two identical fermions can occupy the exact same quantum state at the same time. A quantum state is like a particle's complete address and job description, its energy level, its spin, its orbital path. The principle declares that this specific slot can only hold one tenant. You can think of it as the ultimate cosmic seating chart, where every electron in an atom must have its own unique seat. Without this rule, the universe would collapse into a featureless mush. An atom would be impossible. In a hydrogen atom, the single electron occupies the lowest energy state, the ground floor. Add another electron to make helium, and that second electron cannot simply pile into the same spot. It must take the only other available option, which is the same energy level but with the opposite spin. It is like two people sharing a room but sleeping in bunk beds, one up, one down. This forced separation is what gives atoms their volume and structure. As you add more electrons to build heavier elements, they are compelled to fill higher and higher energy shells, creating the elaborate electron orbitals that dictate all of chemistry. The very reason you do not fall through the floor is because of this quantum refusal. When you touch anything, the electrons in the atoms of your hand are repelled by the electrons in the atoms of the table because they are forbidden from occupying the same space. That solidity, that sense of impenetrability, is not some intrinsic hardness of matter. It is the manifestation of the Pauli exclusion principle in action. But its power extends far beyond chemistry labs. It becomes the last line of defense against gravity in the corpses of stars. When a star like our Sun dies, it sheds its outer layers and leaves behind a white dwarf, a sphere of degenerate matter. All that remains is the star's core, now a seething ball of carbon and oxygen atoms crushed together by immense gravity. The pressure is so great that the atoms are smashed, their electron shells stripped away. A soup of atomic nuclei swims in a sea of free electrons. Here, gravity wants to crush this remnant further, to collapse it into an even denser state. But the electrons push back. They are compressed into an incredibly small volume, but they are still fermions, still bound by Pauli's rule. They cannot all occupy the lowest energy state. They are forced into higher and higher energy levels, creating a tremendous outward pressure known as electron degeneracy pressure. This pressure has nothing to do with heat or nuclear reactions. It is a purely quantum mechanical force born from exclusion. It is this force that supports the white dwarf, preventing it from collapsing under its own weight. There is, however, a limit. An Indian astrophysicist named Subramanian Chandrasekhar calculated that if a white dwarf's mass exceeds about 1.4 times the mass of our Sun, even this quantum rebellion fails. Gravity wins and the star collapses further into a neutron star or a black hole. In neutron stars, a similar drama plays out with neutrons, which are also fermions. Their own degeneracy pressure, neutron degeneracy pressure, becomes the final bastion against total collapse. So from the chair you sit on to the fate of dying suns, an unseen quantum rule of no provides the architecture of reality, a fundamental force of exclusion that gives the universe its form and fights a relentless battle against the crush of gravity. That quantum refusal builds the architecture of matter, but the very stability of that architecture depends on a force of subtle betrayal. The weak nuclear force operates behind the scenes, a master of transformation that quietly reshapes the identity of particles themselves. While its name suggests frailty, its influence is anything but weak. It is the unseen sculptor of the universe's elemental palette, the reason our cosmos contains more than just hydrogen. Without its quiet, persistent work, you would not exist, and neither would the ground beneath your feet. The weak force is unique among the fundamental interactions. It does not bind things together like gravity or the strong force, and it does not orchestrate the grand dance of chemistry like electromagnetism. Instead, it specializes in change. Its most famous act is beta decay, a process where a neutron sitting inside an atomic nucleus spontaneously transforms. In a fleeting moment, one of the neutron's down quarks changes into an up quark. In that instant, the neutron becomes a proton. To balance the books, the process also spits out an electron and an almost undetectable particle called an electron antineutrino. This is alchemy at the quantum scale, the force literally rewriting the recipe of matter. This single, subatomic act of transformation had its most critical performance in the universe's first 3 minutes. After the Big Bang, the cosmos was a seething soup of quarks and gluons cooling into protons and neutrons. Initially, there were roughly equal numbers of each. But free protons are stable, while a lone neutron left to its own devices will decay into a proton via the weak force in about 15 minutes. In that hot, dense early universe, the weak force was constantly at work, not just in decay, but in reverse processes, converting protons back into neutrons through collisions. For a brief window, this back-and-forth transformation kept everything in a dynamic balance. Then, as the universe expanded and cooled past about 1 billion degrees, something pivotal happened. The energy of the particles dropped below the threshold needed for the weak force to operate efficiently. The interactions became too slow to keep up with the breakneck expansion of space. The cosmic conversation froze. In that moment of freeze-out, the ratio of protons to neutrons was locked in, roughly 7 protons for every 1 neutron. This number, set by the weak force's fading influence, became the foundational constraint for all subsequent element building. Those neutrons were the precious seeds for everything heavier than hydrogen. They could team up with protons to form deuterium and then helium in the first few minutes of nucleosynthesis. If the weak force had been slightly stronger, it would have maintained equilibrium longer, converting more protons into neutrons before the freeze-out. The result would have been a universe with far more helium and less hydrogen from the very beginning, altering the entire life cycle of future stars. If it had been slightly weaker, freeze-out would have happened earlier, leaving more neutrons to decay away, resulting in a universe almost purely of hydrogen with no heavy elements at all. The weak force's precise strength wrote the opening line of the cosmic recipe. Its role did not end there. It is the essential catalyst inside every star like our Sun. The primary fusion process, the proton-proton chain, begins with two protons fusing. But two protons alone cannot form a stable nucleus. Their identical positive charge repels them violently. The weak force provides the escape clause. In a rare and crucial moment during a close collision, one of the protons can, via the weak interaction, transform into a neutron. This transmutation releases a positron and a neutrino, and suddenly the pair is no longer two repelling protons, but a proton and a neutron bound together as a deuterium nucleus. This is the bottleneck, the slowest step that governs the entire pace of stellar fusion. The Sun shines because the weak force allows protons to become neutrons, unlocking the energy that has sustained life on Earth for billions of years. In the deaths of massive stars, the weak force takes on a final, dramatic role. As a supernova core collapses, protons and electrons are crushed together under unimaginable pressure. Here, the weak force works in reverse, facilitating a process called electron capture. Protons merge with electrons, transforming into neutrons and neutrinos in an instant. This rapid neutronization is what creates the incredibly dense neutron star at the heart of the explosion, and it floods the universe with a burst of neutrinos that carry away a significant portion of the star's energy. So, from the first minutes of time to the fiery hearts of stars and their catastrophic ends, this quiet, transformative force is the unseen editor of reality. It decides what particles get to be, dictates the fuel for starlight, and forges the very elements that become planets, oceans, and living cells. Every atom of carbon in your body, every breath of oxygen you take, is here because a neutron once decided, under the guidance of this hidden force, that it was time to change. That transformative power of the weak force is only possible because something else holds the very ingredients of reality together in an unbreakable grip. This is the strong nuclear force, the most powerful fundamental interaction in the universe, and it operates under a rule so absolute it is called confinement. It is the cosmic glue, but a glue with a bizarre and counterintuitive property. Unlike every other force we know, which weakens as objects move apart, the strong force grows stronger with distance. Try to pull two quarks, the fundamental particles that make up protons and neutrons, away from each other, and the energy in the field between them increases. It is as if they were connected by an unbreakable rubber band. If you stretch it far enough, the energy stored in that band becomes so immense that it spontaneously creates a new quark-antiquark pair from the vacuum, snapping the band and leaving you with two new bound pairs instead of free quarks. This is confinement. No quark has ever been observed in isolation. They are forever imprisoned inside composite particles like protons and neutrons, bound by a force that refuses to let them go. This unseen prison is what builds the bedrock of visible matter. The force itself is carried by particles called gluons, which, unlike the photon of electromagnetism, carry a charge for the force they mediate. This means gluons can interact with each other, creating a complex, self-reinforcing web of energy that binds quarks together. It is this gluon field that forms the unbreakable bonds. But the strong force's work does not end at the quark level. A residual effect of this interaction, like a spillover of the binding energy, acts as a powerful glue between protons and neutrons themselves within an atomic nucleus. This residual strong force, also called the nuclear force, overcomes the fierce electromagnetic repulsion between positively charged protons, holding the nucleus together against its own will to fly apart. Without this second layer of confinement, no atomic nuclei heavier than hydrogen could exist. The universe would be a featureless sea of single protons. The true cosmic forge of this force, however, is found in the most violent explosions in the cosmos. Inside the stable core of a star like our Sun, nuclear fusion builds elements up to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. To build elements heavier than iron, like gold, silver, uranium, and the iodine in your body, you need a cataclysm. You need a supernova or the collision of neutron stars. In those final, furious moments, a tsunami of neutrons floods the dying star's core. The process is called rapid neutron capture, or the R process. Atomic nuclei are bombarded by a dense sea of free neutrons. The strong force's residual power allows these neutrons to be captured rapidly, one after another, before the unstable nucleus has time to decay via the weak force. This builds up incredibly heavy, neutron-rich nuclei in a heartbeat. Then, in a subsequent cascade of radioactive decays, those neutron-rich nuclei transform into the stable, heavy elements we find on Earth and in our own bodies. Every gold ring, every uranium fuel rod, every trace of platinum in a catalytic converter was forged in a few seconds of stellar chaos, where the confining power of the strong force acted as the anvil upon which these heavy elements were hammered into existence. So the same force that locks quarks away in eternal bondage also unlocks the periodic table, its relentless strength writing the recipe for everything complex in the universe, from the calcium in your bones to the silicon in computer chips. That cosmic forge of elements left behind a signature, a whisper of heat that still bathes the entire universe. This is the cosmic microwave background, the afterglow of the Big Bang itself, and its subtle imperfections are the 27th unseen force. It is not a force that pushes or pulls, but a fossil imprint, a snapshot of the universe when it was just 380,000 years old, a screaming infant cooling into transparency. For decades after its accidental discovery in the 1960s, it appeared as a nearly perfect, uniform glow, the same in every direction. But perfection is not interesting, and it does not lead to us. The true story is written in the tiny deviations, the anisotropies, temperature variations of just a few millionths of a degree. These are the seeds from which everything grew. When the universe was that hot, dense plasma, it was a roiling sea of sound waves, compressions and rarefactions driven by the pressure of light pushing against the gravity of matter. The slight over-densities, those spots where dark matter and normal matter were a tiny bit more crowded, were the crests of these waves. They were held in a tense balance, photon pressure trying to blow them apart, gravity trying to pull them together. Then, at the moment of recombination, when the universe cooled enough for atoms to form, the photons suddenly stopped bouncing off electrons and were set free. That flash of light, stretched over 13.8 billion years into microwave radiation, is what we detect as the cosmic microwave background. The pattern of hot and cold spots we see is a frozen record of those sound waves at the instant they were released. It is a baby picture of the universe's density, a map of its potential. The size of these spots is not random. They tell a precise story. The most common size, a specific angular scale on the sky of about 1 degree, corresponds to the distance a sound wave could travel in the plasma from the Big Bang until that moment of release. This is the cosmic horizon at the time, and it acts as a standard ruler imprinted on the sky. By measuring this scale with exquisite precision, missions like the European Space Agency's Planck satellite have allowed us to take the universe's vital statistics. They tell us the universe is geometrically flat, confirming the predictions of inflation. They give us the exact recipe of the cosmos: 27% dark matter, 5% ordinary matter, and 68% dark energy. The pattern of fluctuations is the Rosetta Stone of cosmology. The slightly hotter spots are where gravity would soon get to work. Over hundreds of millions of years, the extra gravitational pull of the dark matter in those regions would draw in more gas, which would eventually collapse and ignite into the first stars, gathering into galaxies and the vast cosmic web. Every galaxy cluster, every filament of the universe's large-scale structure, can trace its lineage back to a specific, slightly warmer patch on that ancient map. But the cosmic microwave background tells us more than just the beginning. It hints at the very first instant. Superimposed on the temperature map is a fainter pattern, a signature in the polarization of the light. This polarization carries the imprint of the universe's last scattering surface, but also, potentially, of something far older. Within it, scientists search for a specific curl pattern known as B-mode polarization, which could be the direct signature of primordial gravitational waves. These would be ripples in space-time generated in the first fraction of a second during the period of cosmic inflation, the violent stretching that turned quantum jitters into cosmic structures. Finding this signal would be like hearing the echo of the universe's first breath, a direct link to the moment of its birth. So when you look at a map of the cosmic microwave background, you are not just looking at static from the dawn of time. You are looking at the blueprint for reality, a fossilized force field of density that dictated where stars would blaze and where vast voids would stretch in eternal darkness. It is the universe's first and most important map, and we are just beginning to decipher all its secrets. That baby picture of the cosmos holds a secret about the direction of everything. Time itself is an unseen force, an arrow that flies in only one direction, shaping every event from the birth of a star to the fading of a memory. We experience this flow as an undeniable fact, but physics presents a profound puzzle. The fundamental laws, from Newton to Einstein to quantum mechanics, are almost perfectly time-symmetric. If you watched a film of two planets orbiting or two particles colliding, you could not tell if it was running forward or backward. The equations work just as well in reverse, yet our reality is utterly one way. We remember the past, not the future. Eggs scramble but never unscramble. Stars burn out and do not reignite. This is the arrow of time, and it points from order toward disorder, from a special past toward a probable future. Physicists identify three main arrows that all seem to point the same way. The first and most fundamental is the thermodynamic arrow. It is defined by entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Heat flows from hot to cold, never the reverse, because that spreads energy out more randomly, increasing entropy. This is why your coffee cools to room temperature, why structures decay, and why energy eventually becomes useless to fuse heat. This relentless rise in entropy gives time its irreversible direction. The second arrow is the cosmological arrow, the expansion of the universe we observe. As space stretches, it creates more room for disorder to spread, driving the increase in entropy on the grandest scale. The third is the psychological arrow, our own perception of time flowing from past to future. We remember the past because it is a state of lower entropy, a more ordered arrangement of information in our brains that gets recorded as memories. We cannot remember the future because it is a state of higher entropy, a more disordered and uncertain configuration. The deep mystery is not why entropy increases now, but why it was so incredibly low in the past. Why did the universe start in such an exquisitely ordered, low entropy state? This is the ultimate cosmic fine-tuning problem. Imagine a deck of cards perfectly arranged by suit and number. That is low entropy. Shuffle it once and it becomes disordered high entropy. The universe began in a state akin to that perfectly ordered deck. All the energy was concentrated in a hot, dense, and remarkably smooth state, a condition of fantastically low entropy. Since that moment, it has been doing the cosmic equivalent of shuffling itself, spreading out, cooling, and becoming more disordered. If the initial state had been one of high entropy, a chaotic, maximum disorder soup, then nothing interesting would have happened. No stars, no planets, no life. The universe would have been in a state of thermal equilibrium from the start, a static, lifeless fog. So the true unseen force is not time's flow, but time's starting point. The low entropy beginning is the wound-up spring that drives the entire cosmic engine. It is what allows complexity to temporarily emerge. A living organism is a local pocket of order, but it maintains itself by consuming energy from its surroundings and exporting disorder, increasing the overall entropy of the universe. Your life is a process that accelerates the universe's journey toward disorder. The arrow of time, therefore, is not just a measure of change, but the very condition for change. It is the force that allows cause to precede effect, that allows information to be stored, that allows stories to be told. Without this fundamental asymmetry, the cosmos would be a frozen, timeless sculpture. The great unanswered question is why this arrow exists at all. Was it set by the initial conditions of the Big Bang alone, a single, inexplicable fact? Or does the answer lie in the multiverse, where our universe is just one region that happened to start with low entropy, while most others did not? The arrow of time may be the most intimate and pervasive unseen force, the silent current on which all of existence floats, and its origin remains one of the greatest enigmas at the heart of reality. The arrow of time gives our story direction, but who is reading it? This brings us to the most intimate and perplexing frontier of all, where physics meets the mind. The 29th unseen force is not a field or a particle, but the very act of looking. It is the role of the observer in quantum mechanics, and it asks a question that shakes the foundations of reality. Does the universe exist in a definite state until we choose to look at it? At the heart of this mystery is the wave function, a mathematical description that encodes all the possible properties of a quantum particle, like its position or spin. According to the dominant Copenhagen interpretation, this particle does not have a definite property until it is measured. It exists in a blurry superposition of all possibilities at once. An electron is not here or there, it is both here and there, a cloud of potential. The moment you set up a detector to find it, something profound happens. The wave function collapses, all those shimmering possibilities vanish, and a single, concrete outcome snaps into existence. The electron is now definitively here, not there. This transition from the fuzzy quantum world to the sharp, classical world we experience is called the measurement problem, and it begs the question: what constitutes a measurement? Is it the physical interaction with a machine, or does it require something more, a conscious awareness of the result? This is where the line between physics and philosophy blurs. Some interpretations, like the von Neumann-Wigner interpretation, take this idea to its logical extreme. They propose that consciousness itself is the final agent of collapse. In this view, the chain of measurement from particle to detector to computer screen remains in a quantum superposition until the information is registered in a conscious mind. Only then does the wave function finally settle. It suggests that reality, at its most fundamental level, is participatory. We are not passive witnesses to a pre-existing cosmos. Our observation is an act of creation, a force that crystallizes one history out of a sea of maybes. This is a staggering proposition. It would mean that the moon is not truly there when no one is looking, that stars flicker between existence and potential until a mind somewhere turns its attention to them. Critics argue this places far too much weight on human consciousness, a phenomenon we barely understand. They point to other interpretations like the many worlds theory, which avoids collapse altogether. In that view, every possible outcome of a quantum event actually occurs, but in a branching multitude of parallel universes. The detector, the scientist, and their consciousness split along with the particle, each version experiencing a different, definite result. There is no collapse, just an ever-diverging tree of realities. Yet the question lingers, why does our experience feel so singular and definite? The act of observation, whether by a machine or a mind, remains the mysterious hinge upon which the quantum world turns into the solid world we know. It forces us to confront a possibility as beautiful as it is unsettling. The most fundamental unseen force shaping reality might not be out in the distant cosmos, but within the silent theater of our own awareness, the light of attention that brings the universe into being, one observation at a time. If consciousness is the final observer, what is it observing? The 30th unseen force is not a single entity, but the ultimate framework that could contain them all. It is the multiverse, a concept that redefines reality by suggesting our entire cosmos is just one page in an infinite cosmic library. This idea emerges from three distinct lines of thought, each painting a different picture of a reality beyond our own. The first stems from cosmic inflation. We know our universe underwent a period of hyper-expansion in its first moments, but what if that inflation never truly stopped? The theory suggests that in some regions, inflation could end, creating a bubble of stable space-time like our universe. In other regions, it could continue forever, with new bubbles constantly budding off. Each of these bubble universes would be causally disconnected from the others, forever out of reach, and each could have different physical constants, different dimensions, even different laws of physics. In this eternal inflation scenario, we simply live in one bubble where the numbers allowed stars and planets to form. The second vision comes from string theory. To make the mathematics of strings work, the theory requires extra spatial dimensions, curled up so small we cannot perceive them. But there are potentially an astronomical number of ways these dimensions can curl and fold, each configuration yielding a different set of physical laws and constants. This is the string theory landscape, a vast, abstract terrain of perhaps 10 to the power of 500 possible universes. Our universe, with its specific constants, would correspond to one tiny valley in this unimaginably vast landscape, one stable configuration among a near infinity of others. The third, and perhaps most provocative, is the quantum many-worlds interpretation. It proposes that every time a quantum particle faces a choice, the universe does not choose. Instead, it splits. At every quantum event, the wave function does not collapse, it branches. One reality continues where the electron went left, another branches off where it went right. This happens for every particle, everywhere, all the time. In this view, every possible outcome of every quantum event actually occurs, spawning an endless, ever-diverging tree of parallel histories. There is a universe where you turned left instead of right this morning, a universe where the dinosaurs never went extinct, a universe where every conceivable variation of physical law is played out in some branch. While these ideas are currently untestable, they represent a profound shift in perspective. The multiverse is not merely a science fiction trope, it is a serious, albeit speculative, attempt to solve the ultimate riddle, the fine-tuning of our universe. The exquisitely precise constants that allow for our existence seem like a miracle, but in a multiverse where every possible set of constants is realized somewhere, it is no longer a miracle, it is a statistical inevitability. We do not live in a special universe, we live in a habitable one, and we could not observe anything else. The multiverse transforms the question from why are the laws so perfect for life, to why are we in this particular part of the multiverse where they are. It suggests that the deepest unseen force might be a principle of cosmic selection, where our local reality is just one possibility rendered real by the simple act of our being here to see it. This idea culminates our journey through the unseen. From the dark matter scaffolding galaxies to the quantum static birthing them, from the arrow of time giving our story direction to the observer who reads it, we have traced the hidden architecture of reality. The multiverse asks us to take the final, dizzying step to consider that all these forces, all these mysteries, might be local bylaws in a single cosmic neighborhood, one page in a book with infinite chapters. It is the ultimate unseen framework, the silent canvas upon which our universe, and perhaps countless others, are painted. We have traveled from the invisible scaffold of dark matter to the phantom push of dark energy, from the quantum static that seeded galaxies to the conscious observation that might bring them into focus. This journey through 30 unseen forces reveals a universe far stranger and more magnificent than the starry sky suggests. The cosmos is not built from light and dust alone, but from hidden fields, quantum rules, and informational threads woven into the fabric of reality itself. Some forces, like the strong nuclear force or the Pauli exclusion principle, are the well-tested architects of our tangible world. Others, like cosmic strings or the chameleon field, remain brilliant possibilities waiting in the wings of science. And still others, like the multiverse or the role of consciousness, stretch the very limits of imagination, challenging us to redefine what is real. The ultimate lesson is clear: to understand the universe, we must learn to see in the dark. We must listen for the whispers of gravitational waves, feel for the tug of unseen masses, and decipher the fossilized light from the dawn of time. Our reality is a grand performance, and we are only now beginning to meet the stagehands, the directors, and perhaps even the other audiences in the infinite theater. So tell us, which of these unseen forces captures your imagination the most? Is it the ghostly sea of actions that might be dark matter, or the cosmic strings that could be scars from creation's first second? Let us know in the comments below. If you want to keep exploring the deepest mysteries of space and time, be sure to subscribe. The universe is full of secrets, and together we are just beginning to pull back the curtain.